this is going to be called differentiability. Differentiability. Whoop, moving the screen. Okay, ability. There we go. Okay, so differentiability, here I'm just going to kind of define in a more formal sense what is it when we're talking about on this subject of like a function being differentiable, like a multivariable function being differentiable, and what it has to do with tangent planes. Okay, so what we're going to do, starting off the formality, is say that assuming, because we always have to assume some stuff, so assuming that f of xy is defined in disk D, disk capital D, okay, containing a point AB, and our partial derivative with respect to x of AB, and the partial derivative with respect to y evaluated at AB exist, then we can say that f of xy is differentiable, so I'll just abbreviate differentiable, okay, at AB, A comma B, and, or if it is locally linear. Okay, so this in another sense is basically means, so aka, I'll just say, is f of xy is equal to the linear approximation, right, and then plus the error. Okay, so this is kind of like a rewritten form of the other way where we had error by itself, and we just subtracted the linear approximation from our function. So again, this is our approximation, and this is our error. I can't spell. Okay, hold on. Error. I can spell, I just can't write. Okay, there we go. So we have that, and then, so I'll rewrite it up here. So we have this part so far. So f of xy is equal to L of xy plus E of xy. And then this is the important part where E, well, I'll just write, yeah. So where our error satisfies the following. And we've already gone over this, but here I'm just writing it all together. So where the limit, it satisfies that the limit as xy approaches AB of E of xy over square root of x minus a squared plus y minus b squared, and again that's the distance between the 2 points, is equal to 0. Okay? Alright, so that's basically it, and furthermore, I'll say, this is kind of like extra, the tangent plane, which we've already learned right now. So the tangent plane to the graph, I just got lazy and didn't say to the graph at the point A, B, f of AB is z is equal to L of xy. So this is our linear approximation, which gives us the equation for the tangent plane, is f of AB plus f sub x at AB times x minus a plus f sub y at AB times y minus b. Okay, so that's basically on this whole slide. This is like the takeaway from this entire section about differentiability and the tangent planes. Okay? Alright, now let's do an example. What we're going to do is find the equation of the tangent plane of wait for it, okay, tangent plane for f of xy is equal to 5x plus 4y squared, and then we'll say at the point 2, 1, okay? Alright, so first of all, to write the equation of the tangent plane, let's write the general like equation form without anything plugged in. So we know that L of xy is going to be equal to f of AB, okay, plus f sub x evaluated at AB times that x minus a plus f sub y evaluated at AB times y minus b. Okay, so first of all, we have to, what do we have to do here? So here's our f of xy, but the first thing that we have to do is actually identify our a and b. What are those? So we're given that the point is 2, 1, so a would be 2, and b equals 1, okay? And then, so we're going to have to plug in 2, 1 into our function to find this f of ab. So f of 2, 1 is going to be equal to 5 times 2 plus 4 times 1 squared. Right, so that's going to be equal to 10 plus 4, which is 14. Okay, so we found that. Right, so this is our f of ab. Okay, so that's that first part. And now, for these ones, for our f sub x and f sub y, we have to differentiate, take the partial derivatives of our original function. So f sub x is going to be the derivative, partial derivative with respect to x of our original function. Okay, and when we do that, we just get out a 5, right? Because the y terms go away, and then we pull out that coefficient of x. And then, secondly, we have f sub y. That's going to be the partial derivative with respect to y of our function. So we have something like that, right? And the x term is going to go away because that's like a constant. And then we have an 8y here, okay? And furthermore, we have that if we're going to plug in that 2, 1, our ab, right, into each of those, we get f sub x of 2, 1 is just going to equal 5, because that's constant 5. How about f sub y at 2, 1? Then we plug in a 2 for the x spot and a 1 for the y spot. We only have that one y spot, so we're going to do 8 times 1, which turns out to be an 8. Okay, so this is the f sub x at ab. Okay, this is the f sub y at ab. Okay, so we have those two things, the 5, the 8, and the 14. Okay, and then we know that a is equal to 2, a is equal to 2, and b is equal to 1. Alright, so let's plug in all of this information on the next slide. So we have that f of 2, 1 is equal to 14, f sub x of 2, 1 is equal to 5, and f sub y of 2, 1 is equal to 8. And then we know a equals 2 and b equals 1. Alright, so let's plug this in. We get L of xy is equal to a 14, right, that's in for that spot, plus our f sub x, so that would be a 5 times x minus a, which is a 2, okay, and then we have that added to our f sub y at 2, 1, so that would be 8 times y minus b, and b is now 1, so we plug in that. Okay, so now let's just simplify, and we get that z, which is also the same thing as the linear approximation, right, that's going to equal 14 plus 5x minus 10 plus 8y minus an 8, okay, and then if we continue here, we get 14 minus 10 minus 8, so that would be 14 minus 18, so that would be a negative 4, and then we have plus 5x, and then plus 8y, okay, so that's basically it. If you want to rearrange, swap the negative 4 and the z, you can, so then we could also get like 4 equals 5x plus 8y, and then minus a z. Either answer works, they're the same equation.